a book in lab.
Someone who was working with me.
Oh, that's mine.
Oh, it's yours?
I recognize the little scratch on the bottom.
You recognize that scratch?
How much does it resell for on
Anything
Amazon?
I
that
was
comes
gonna
out of your
say.
mouth, I think, is a lie.
Now I think I might have to get lunch.
I think you gotta get lunch out of that.
We don't resell.
That's worth Chipotle, I say.
Yeah.
Chipotle.
If that's my book, I'm going to kill you for it.
Chicken.
Okay, now that we got that out of the way, let's go back here. Let's go back and talk about some more reduction. We got the carbon crude, I slapped up a mechanism, and then you're done. So, in general, as we talked about last time, when you take a carboxylic acid and reduce it, you go first through an aldehyde, which is pretty reactive to reducing agents, so it doesn't stop, and then it reduces again to the alcohol. And as far as the reducing agents that you can use for this, we had lithium aluminum hydride H3O+. That was one possibility. Another one that can be used, sodium borohydride won't do it, but BH3 will do it. So just plain BH3. The solvent is THF, which is an ether. THF is a cyclic ether. It looks like that. So BH3, THF, and that would be step A. And then again, there's an H3O+. So those are the two probably most common ones. And they're both hydride reductions. And I gave you guys one mechanism that sometimes books will show where OH- is the leading group. And then the one that's probably the more plausible one, where the leading group is actually a complex. And that's kind of the one that your book goes into. I will not ask you this mechanism. Okay? It's not one of the important ones in the chapter. So you can see it in your book, you can kind of see how it works. It's not one of the things you'll be seeing on this. Okay, so this works great if you want a primary alcohol. But oftentimes, we're going to make this go away. I see what's gone here. Okay. Oftentimes, that's not what you want. You'd like to get to an aldehyde, because an aldehyde is very useful. As you guys have seen, you can do grignards with it, you can do all sorts of things with it. So, say you wanted to get to the aldehyde. Well, with the reagents I just gave you, you'd have to do this. You'd have to go from the carboxylic acid to the alcohol, because we don't have any other options. And then you have to turn around and go partially backwards with PCC, which seems stupid, right? It seems like there's got to be a better way than to go forward all the way only to loop around and go halfway back, right? That's not very efficient. The problem is that the carboxylic acid is less reactive than the alcohol, or than the aldehyde. So, the fundamental issue you're going to run into trying to find any reagent is that COOH is less reactive than the aldehyde. So because of that, you need a good reducing agent to reduce the carboxylic acid. Right? It's got to be pretty powerful because it's not very reactive. Well, a good reducing agent is going to kill the aldehyde. So you're stuck. There is no good way to do this. But there is a trick. So, the workaround. I don't know that it's much better. But the workaround that people use is they take the carboxylic acid and they turn it into the acid chloride. So this would be SOCl2 impurity. So you make the acid chloride. That's a reaction that is really high yield. It goes really easily, really high yield. The acid chloride is very reactive. So then what you do is you use a reducing is too weak to reduce an aldehyde. So what we've done is we have changed the carboxylic acid, which is not reactive, into something that is really reactive. So we can use a wimpy reducing agent. It'll pass through the aldehyde, and then it stops. Okay? The reducing agent most commonly used for this, it's a weird one. Lithium, aluminum, triterbutoxy hydride. So this is lithium, aluminum, triterbutoxy hydride. And that can get you the aldehyde. Whether that's more efficient than doing this roundabout way, hard to say. But that typically is what people do. I think they yield to just overall a little bit better. Okay, but you won't find, unless there's some specialized reagent out on research somewhere, one that will go stop at the aldehyde because of that fundamental reactivity problem. Okay. All right. So now the derivatives. The derivatives chapter, well, it's the second half of this chapter. It's the one with tons of reactions in it. I guess if you counted them up, I don't know, maybe there are 40, 50 reactions in it. And you have to know them. But what we're really looking at with the derivatives is fundamentally one reaction, really two possible mechanisms in just different nucleophiles is all we're doing. So with the derivatives, let's take a look at the possible compounds we'll be looking at. It's these guys right here. So we have acid halides, hydrides, esters, amides. Nitriles we're going to kind of take as their own separate grouping. They don't look at all like the top four. The top four, you can see there's a carbonyl and then something next to it. Nitriles are always included in this grouping because anytime you do a hydrolysis of any of the derivatives, you get a carboxylic acid. And the same is true for nitriles. So they actually have a very similar chemistry, even though they look nothing like a derivative. So we'll run through the top four, and nitriles will kind of be our side at the very end. All the derivatives have this basic structure. And all of them are going to come from somewhere in their past life a carboxylic acid. We have worked with amides. You guys have made amides in the amines chapter. They came from a carboxylic acid, which we turned into an acid chloride, which we treated with an amine. You'll see esters. We just saw them 2 days ago. They came from carboxylic acid and alcohol. So all of those guys are going to come from a carboxylic acid. Nitrile, separate deal. What you do with a derivative, this is really R, C double bond O, and something that can be a leaving group. And that's the key thing, as we go through this reaction, these reactions, I'm going to start to get really repetitive. I'll say, okay, the nucleophile attacks the C double bond O. Electrons go up, they come down, they kick out the leaving group. We'll say that over and over and over today and prior next time. So what happens is nucleophiles will attack at the carbonate. As we've always seen, we break the pi bond, the electrons go up. And if we have this, and here's our nucleophile, here's our leaving group. Then electrons can come back down, reform the C double bond O, and kick out the leaving group. So almost every reaction of those 40, or whatever it is like this. The only difference is going to be how good's your nucleophile. If it's really good, it can attack straight out. If it's not so good, then we're going to probably have a protonation step. We'll be protonate, we're going to have to move hydrogens around, N-propane. Okay? That's really the only difference. We either attack straight out, or we have a proton that we have to deal with that moves around. And you guys have seen that before. So what is really 40 reactions isn't really 40 reactions. If you learn the mechanism, think about it, it's much fewer than that. Just different nucleotides. Okay, so when you're reading it, don't hyperventilate. It's okay. All right. The first thing we have to do is a crazy nomenclature of these. So let's go ahead and tackle it. Okay. The acid halides. With all of these, we're going to be basing the name on the parent carboxylic acid. So remember, we go from a carboxylic acid to whatever it is, different Y groups. So we're going to name the carboxylic acid first, and then we'll just tack on different endings, depending on what kind of functional group is there. So with acid chlorides, or acid halides, you are going to find the longest continuous chain that includes the carbonyl group. And let's go ahead and we'll just work on the example as we go through it. So I'm just going to write it up here. This first one. There it is. All right. Going back. So you're going to find your longest chain that includes the carbonyl. So there it is. And then we're going to number it. You start at the carbonyl, which is great for numbering. You don't even have to think. So here's 1, 2, 3, 4, 5, 6. Then we're going to name the parent carboxylic acid. So, as far as the carboxylic acid goes, go ahead and give me this name. Don't forget the metals. Okay, 4,5-dimethyl. And then the carboxylic acid part. Hexanoic acid. Good. Okay, so that is the basis. The carboxylic acid that was the basis. Only what we're going to do, since it's not a carboxylic acid for real, you drop thick acid, so you erase it, and you add the ending YL, then a space, and then the halide. So it's 4,5-dimethyl hexanoyl. It's a little weird. Yl chloride. Okay, so it's not too bad. Just drop the ic acid, add YL, and then the halogen. Questions? Okay. Why did that show up as an H? Oh, I see. It's a DR on the other side. Naming that one. On this one, I think the hardest thing is dealing with that aldehyde right there. We learned that when an aldehyde is a substituent, it's what kind of group? Formal group. It's a substituent if, an example we did last time, we had this long parent chain, I think there was a carboxylic acid, a double bond, and like an NH2 out here, whatever, and it was hanging down here, right? So it would not be, our parent chain was here, and this guy was not part of the parent, right? That's not the case there. Okay, I start here, right? I go on, I can encompass that. So you actually take that carbon and count it as part of your parent. Okay, you don't stop here and then have a formal, because that carbon can be part of the parent. Okay? All right. So with that in mind, let's name it as a carboxylic acid first. What am I going to do? It's like a number, huh? 1, 2, 3, 4, 5. All right.
One bromide.
Now I don't want to do formal because I actually encompassed that. It's only formal if this whole unit, that whole thing, including the carbon, is not part of my chain. It's dangling off somewhere. So it's part of my chain. I've got really a double bond O substituent. What is that?
It's a ketone.
It's a ketone, which is oxo. Good.
Oxo.
So 5-oxo. Now what?
What's 1-bromo-5-oxo?
And
3.
yeah, pent-3-ene.
Well,
Wait, it's a little weird, huh? And do I need E or Z? Do I need to worry about that? Yeah,
Yes.
which is it?
E.
E. I'm just going to put it out front. For it. Okay, so as a carboxylic acid, it's 5-oxo, pent, 3-ene, acid. Everyone okay with that? Okay, the rest of this is easy. It's actually an acid bromide. So we get rid of the acid and go YL space bromide. Okay. Any questions? All right. Let's go ahead then and talk about anhydrides. Anhydrides, there are 2 types. The kind that you see in your text to name, and the kind that I will give you, are what are called symmetrical anhydrides. So an anhydride in general looks like this. When we talk about symmetrical or unsymmetrical anhydrides, what we're talking about is these R groups right there. If both R groups are the same, that is a symmetrical anhydride. If the R groups are different, then that is an unsymmetrical anhydride. As far as the nomenclature, the unsymmetrical anhydrides are a little difficult to name. I'd have to actually go look it up. They're weird. We're going to be doing both R groups are the same. Anhydrides are useful as intermediates in reactions. And when the nucleophile attacks, it can attack either here or here. Right? Both places, they're essentially equivalent. The advantage of having a symmetrical anhydride is you get the same product regardless of where it attacks, right? Because the R groups are the same. If you were to use as your intermediate an asymmetrical or an unsymmetrical one, then you can get 2 different products. So as intermediates, people tend to use the symmetrical ones. So those are the ones we're going to focus on. Okay, so since they are the same on each side, what we are going to say is that it really is, you kind of take a look here at this overlap, it's really 2 of the same carboxylic acid. See that there? The overlapping there, there's a carboxylic acid, and then here, that's the second carboxylic acid. They share an oxygen. Okay, but it's 2 of the same carboxylic acid. So what we're going to do is really name the carboxylic acid that is the same on both sides. So what you do is, and let's again flip forward and we'll do our first example as we go through this. I'm going to write it up. Okay. So you determine the number of carbons in the longest continuous chain that includes the carbonyl group. So I'm going to be naming that. And basically my
Wait,
parent.
isn't that an
But
ester?
I messed it up, huh?
Isn't that an ester?
Yeah, I messed it up. Better?
Much better.
Yeah, now it's better. Okay, So just focus on just one side, since both sides theoretically are the same. So you find the longest continuous chain. Then you name it as a carboxylic acid. So this is 1, 2, 3, 4. If this were a carboxylic acid, so this weren't here, and that was just an OH, it would be 3-methyl butanoic acid. So it's based on 3-methyl butanoic acid. What you do to show that it's an anhydride is you get rid of you use the oic suffix, you get rid of acid, and add the word anhydride.
That's it.
So it's 3-methyl butanoic anhydride. So all you have to do is erase the word acid. The hardest part about these names, in and of themselves, they are not hard individually. It's keeping track of when do I keep the OIC, when do I get rid of it and add a different ending, that kind of thing. Okay? Let's try another example. Try that thing. I'm just going to put the answer up. I'm not actually going to do it. So I'll put all the substituents out front. 4-bromo. Then there's a cyclopentyl. That'll be next. And that's at number 5. 4-bromo, 5-cyclopentyl of methyl at number 3. And then we have to loop around. I ran out of room. 1, 2, 3, 4. It's 5 carbon long, major chain.
Pentoic acid.
So it's pentanoic acid. But we're getting rid of the acid and writing anhydride. Okay on those? All right. Let's do esters. I had the hardest time when I was learning OCHEM, naming esters. I don't know why, it just wouldn't stick. It's not like it's hard. I couldn't figure out which R group to put first. And once I practiced it for about 15 years, I got it down pretty well. It literally, even when I was first teaching it, I'm like, oh, which R group goes first?
That's confusing.
It's not hard. I don't know what the problem was. Okay, with an ester. I'm just going to put R prime there. Whenever you see like a little R prime, all that's implying is it's a different R group. It could be the same, it could be different, whatever. What you do with this is you name this first. This comes first in the name. So the alkyl group that is attached to the oxygen comes first. So it's going to be R prime name, and then a space, and then the carboxylic acid derivative part. Okay, so the very first word in an ester name is going to be butyl, pentyl, separate, that kind of thing. It's that alkyl group, it's the R prime name. So, let's do what we've been doing before and work on our first example as we go through this. So, it's this guy right here. Okay. So, we will first name the group on the oxygen, right there. What is it? So it's an ethyl something. There's ethyl and then a space. Then we have to name it as the other part is a carboxylic acid. So doing that, I have 1, 2, 3 methyl. Butanoic acid. Okay, that's kind of the what created the ester. But now we're going to fool around with the ending. So, we determined the number of carbons in the longest chain. We numbered it, starting with the carbonyl. Okay, here's number 4 is what we care about. Use the name of the parent carboxylic acid. Drop ic acid. So we are going to drop the ic acid. And then we're going to add 8, A-T-E. Right there. That is signifying it's an ester. So it's ethyl 3-methyl butanoate. Okay, questions?
What was the space?
What's what?
What was the space?
That's just how they do it. They always just put a space in between this first alkyl group and this. There is a space right there. They don't run it together. And I think that's probably to differentiate that ethyl is not being part of the parent chain. It's not on the other side of the carbonyl. All right. Let's see what you guys can come up with for number 2, second. Huh? A little scarier looking. I think I'll go draw this one up. All right, what is the very first word in the name? Propyl. So the propyl is just signifying this group. That was easy. The rest of this, a little bit tougher, but not too bad. Start numbering here.
It's 5, 6, 7.
5, 6, 7, 8, 9, or 9 carbons. Okay, we got to do these substituents. 2 methyls, they're easy. What is that thing at number 7? It's an ethoxy. Good. So that will come before our methyls. So we have 7 ethoxy.
5, 6,
6,
9
9 methyl.
methyl.
Good. Then it's 9, so no something. Okay, no.
5,
Then I have to do 5.
E.
Parent came from enoic acid. Enoic acid.
It's
Oh,
not
I got
5.
to do E or Z, don't I?
It's 5E.
This goes up. That's number 1. Number 1's down. It's 5E. So we'll just go E there. Okay, but it's not carboxylic acid. It's an ester. So we get rid of the acid
You know it.
and put. Yes. If you wanted to put the E in front.
You have to put right before the
Right
7.
there, right before the 7, yeah, right there. Because the E pertains to the carboxylic acid parent. All right? You're almost done. 2 more to go. Okay, amides. Amides, we have several different styles, and they are named slightly differently. So first, let's talk about the different kinds of amides that you might run into. You can have a primary amide, secondary, or tertiary amide. Primary amides are going to look like this. So you have what had been your carboxylic acid parent and an NH2. Those are the ones we ran into with a reaction that we just learned about 2 weeks ago. It was the Hoffman rearrangement, right?
Slide
It
it
had to be a
over.
primary amide, and so that has an NH2. The secondary amide has the carboxylic acid part to a nitrogen, but the nitrogen now has an RB on it. So you'd make that from an acid chloride and a primary amide. Tertiary amides, carboxylic acid part, and then the nitrogen would have 2 alkyl groups on it. They may or may not be the same. They don't have to be the same. Now, as far as nomenclature goes, these guys have their own nomenclature, primary amides. Secondary and tertiary are treated the same. So we'll treat them together. Okay. So, for the primary amide, we've got our example right there. You're going to determine the number of carbons in the longest continuous chain, including the carbonyl group. So, wow. Do I want to rewrite that? I probably do. Up, over, my bet is it's that guy. Am I right? So this would be 1. This is an NH2. So that's 1. That's 2. 3, 4, 5, 6. Or 2, 3, 4, 5. So we're going this way. 3, 4, 5, 6.
That's a sec view.
And then we just numbered it. Now we're going to name it as a carboxylic acid. So pretend the NH2 is not there. I have a methyl hanging off of there, and then what's this thing?
Sec butyl.
It's a sec butyl. Okay, so we will go 3 methyl. No, we won't. Sec butyl comes first.
Shit.
2 sec butyl,
Oops.
3 methyl,
Hexanoic acid.
hexanoic acid.
And
Okay, only it's not a carboxylic acid, so we're going to drop the oic acid. Now we're dropping the O as well, which is kind of a new thing. So it's just hexane, and we add the word. I think the reason they dropped the whole thing is because then it would look like this. Hexane O amide. That just looks weird. IUPAC doesn't typically do that 2 vowels in a row. So that just looks strange. And so you drop the O as well. So they're easy to do. You just do your carboxylic acid parent and change the oic acid to an amide. So, okay? Questions on that? All right. You need that information to do the more complicated ones. So, now we're going to tackle secondary and tertiary amides. We're going to name them just like we did primaries. The only difference is now we have to deal with substituents that are on the nitrogen, right, which they were not there before. So that actually is not that hard to do. So secondary and tertiary amides, what we're going to do in a nutshell is name them as N-substituted primary amides. So we're going to have these R groups here, this one and that one, let's say if we're doing a tertiary, they are just 1 or 2 more substituents, only they're not on the chain, they're on the nitrogen. Okay, so it's nothing that complicated. So what we're going to do is we'll name them, we'll cite them alphabetically with all the other substituents. They go in the pile of all the substituents, only they don't get a number because they're not on the chain, they're on N. So they get N as their number. Make sense? Okay, and when you see a number, if I see like a 2, a 3, a 7, I know that's on the chain. If I see an N, like N butyl, then I know the butyl group's on the nitrogen. It's that hard. So, this guy right here. In terms of substituents, figure out what we have. My chain's going to loop around towards the chloro, it looks like to me.
Yeah.
So, my parent is going to be here like this, and then coming down like that. Okay? Numbering it, I have 1, 2, 3. I have a methyl at 4 and a chloro at 5. So, what we'll have is, I'm just going to kind of pile them up so I can alphabetize them in a minute. A 5 chloro, a 4 methyl. What's on the nitrogen? Another methyl. So a 4 and an N. Okay? And then what else is on the nitrogen?
Cyclohexane.
Cyclohexane. Okay. And the parent carboxylic acid is 1, 2, 3, 4, 5. So it's pentanoic acid. Okay, let's put it all together now. We have 5 chloro, N, cyclohexyl, and I'm just alphabetizing the substituents there. And then we have a methyl on N and a methyl on 4. Well, if it was a methyl on, say, 2 and 4, you'd go 2,4 dimethyl, right? And now it's just N4 dimethyl. And there doesn't seem to be any consistency between which one comes first. You'll see some papers and some books do 4, N, some do N, 4. I don't care what you do. Okay, just make sure that it's appropriate, they're all there. And what did we say it was? A pentanoic acid? So it's based on pentanoic acid. We get rid of oic acid. It's pent. Pentamide or pentanamide, however you want to pronounce it. Okay, so they really aren't that difficult to make. All right. Questions so far? Okay, last one. This is nitriles, which were kind of the weird ones that we're going to treat all separately. And you know, I think actually this is a big moment in your lives. You don't know it, but I'm pretty sure we do carboxylic acids, we do derivatives, we take your test, right? And then we do alpha carbons, and then biochem. This is your last nomenclature right here, ever. So this is like a big moment, right?
We should have brought cupcakes.
No one cry, it's okay.
2 of us are recording this moment for posterity.
I'm almost sure I don't do any nomenclature in that alpha carbon chapter.
You better.
If she does.
You don't believe me? I'm pretty sure I don't. I think this really is it.
It would be hard to do that.
Okay, so dun 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 dun. Nitriles. We end with nitriles.
One of us is putting it on YouTube for everyone to see.
Okay. Yeah. Okay.
That thing.
We'll make that a practice one. I'm gonna have to rewrite this guy.
What was that thing?
This is awful. I must have been a bad mood when I thought this.
You're like, yeah.
This'll teach him.
It's okay.
No.
We'll end like this. Okay. So take that. All right.
You're learning stuff.
Okay, so
Students
that's
name
it
that.
right there. What you do for a nitrile, she gets the number of carbons in the longest continuous chain, blah, blah, blah. That includes the carbon of the nitrile. That's the biggest mistake people make, is they leave the nitrile as its own little separate substituent. It's not. It is part of the parent. So I'm going there. You want to include that carbon, just like you would a carbonyl. Okay? Then we go into our longest chain. I think it's this one.
Yeah.
Okay, like that. That's what it looks like.
I say a chloro and a
Okay, so
isobutyl.
this really isn't as mean as it looks. Then you number the parent chain beginning at the nitrile. So 1, 2, 3, 4, 5, 6, 7.
I can name it.
Okay. And then we're going to name it, combining the words alkane and nitrile. So how many carbons? We have 7 carbons in it. So with 7 carbons in it, it is the alkane is heptane. And then the word nitrile. Well, I got to put substituents in front. That's it. It's the carbon, however many carbons long it is, it's its alkane name. And then the word nitrile. And then you got to put substituents in front.
3
So I'm
chloral.
going to go ahead and name them. So,
3 chloral.
3 chloral, good. We'll make it teeny. 3 chloral,
5 methoxy.
5, well, let's do isopropyl first, methoxy next.
Okay,
So
4
4
isopropyl.
isopropyl,
5 methoxy.
5
Gosh, my camera can't even pick
methoxy.
this.
Professor, why don't you do isopropyl?
She wrote methoxy in shorthand.
Oh, because it's alphabetized by an I. Sec, but like things like sec and tert, you don't count those. Iso is counted. So iso and neo are the 2 that are
Well,
counted.
5's ethoxy, right? Shouldn't that?
No, this is a methyl, I think. Isn't that just one?
Yeah, it's epoxy.
Oh,
Just methoxy. Yeah, it's just one.
Methoxy.
Okay? So individually, these are not hard, but you just have to keep track of what indie goes with what. That's the hard part. And then the fun. You're just going to have to memorize this next thing. Just don't fight it and memorize it.
Don't fight it, let it
Don't
in.
fight it. Yeah.
Let it happen.
All right.
Go to your happy place.
Go your
I
happy
would
place.
really like that. I'm going to do something real fast, see if I can save myself some writing. Hold on. I'm going to go to the ones with the name on it. There. Okay, you memorize these. When these are on a cycloalkane, the naming gets weird, which is kind of no surprise. We've seen that for a while now. So you guys are going to want to memorize these right here. Make some flashcards and just memorize them. Those are the parent names. Obviously for cyclohexane, if it was on a cyclopentane, it'd be a little different. It's a cyclopentane instead. Okay? But memorize those. So the first one we've seen before, cyclohexane carboxylic acid. If it's an acid chloride, cyclohexane carbonyl chloride. And there's no logic, just memorize it. If it's an ester, it's the alkyl group is still in front, methyl in this case. Cyclohexane carboxylate is the parent, cyclohexane carboxylate. If it's an amide, cyclohexane carboxamide. And then cyclohexane carbonitrile. I don't know where these came from, but make 5 flashcards. Yes?
Is this one slide posted online?
You know, it's not, but I can do that. You guys, if you just post it online?
Yes, please.
Okay.
What?
Remind me in lab, okay, before I write all over myself. You guys who have lab in the afternoon, remind me and I'll do it while you work.
For 2' and 3', we just go ahead and do the same thing we did for.
This would be for, we're talking about amides,
Yeah.
right here? Yeah, same exact thing you do. So you'd have numbers for any substituents on the ring, and then N for any substituents on nitrogen. But the naming's still all the same, it's just the parent name is really weird. So looking like this guy, right here, you can see there's a nitrile on there. So my parent is this whole thing, right here, and there are 7 carbons in the 6th cycle. So the base name is cycloheptane carbonitrile. And then you just do the substituents. We're going to go clockwise to keep numbers small. So it's 3, 4, 4 trimethyl, 6 hydroxy. This lower one here, it's an amide, it's substituted, so we'll have an N with that substituent. The amide parent itself is going to be cyclo whatever ane carboxamide. And it's 8 carbons, so cyclooctane carboxamide. Yeah, I was pointed at you.
What we had, amide parts of the early nitrogen parts in the ring.
Ooh, if you have the nitrogen in the ring, it depends how it's placed in there. If it's just like this, kind of like that, it names just as a neem would. Okay? But if it is like this, say it looked like this, is that the kind of thing you're talking about? Okay. If the amide is in the ring, it is called a lactam. Those are called lactams. And you have a similar thing if an ester is in the ring. Those are called lactones. And I will not have you guys name those. Okay, they have their own little specific, they're usually are common names for the smaller ones, and they're based on, the nomenclature's based on the common name. Okay, so I won't ask you within a ring, I won't do that here. Okay, I'll do it hanging off a ring like those are though. Okay, so this one here, it is N-ethyl, there's an ethyl group on nitrogen. At number 3 is a formyl group hanging off of the ring, and then cyclooctane carboxyl. And I'll post those names up for you guys, if you guys remind me in the afternoon.
In terms of priority, like, how do we know which one is right?
Oh, as far as the priority, they follow the same priority rules as that sheet. No difference there. All right, let's do some chemistry with these things. How I'm going to divide this out is, once I find it, I'm going to do it as functional groups. So we'll look at acid halides, for example. Look at how to make them, which we already know. And then we'll look at the reactions of them. As far as making them, I think we know how to make every single one of these derivatives. So we'll quickly review it, and then we'll do their reactions. And we're going to be essentially going, the order we'll be doing is the acid halides to acid anhydrides, the anhydrides to esters, the amides. And then nitriles will be very good. What we're following there is an order of reactivity. So with the acid halides, they are very reactive. They will do a lot of reactions. And so we'll look at a few of them. We'll put various nucleophiles in. But keep in mind, you could put a different nucleophile in. It'll do the same mechanism, just give you a different product. Okay? Anhydrides are very similar, but not quite as reactive. As we get down into esters and amides, what we're going to see with these guys, they're less reactive. So what's nice is that they have less reactions to memorize. That's a kind of a bonus. But we're typically going to need good nucleophiles or catalysts. So our mechanisms are going to switch a little bit here. For the first two, I probably won't be using much in the way of a catalyst. Certainly not for the top one. But then as we go down lower, we're going to do a lot of minus H plus H plus kind of chemistry because they just are not very reactive. All right. Let's start out with acid halides. As far as the prep goes, it's pretty consistent. You have a carboxylic acid. If you want to make an acid chloride, we studied this one before, SOCl2 pyridine, that's what we looked at last time. You guys have the mechanism. That makes the chloride. If you want to do an acid bromide, EBR3 in pyridine, and I'm not going to talk about that mechanism. Very similar. It does the bromide. People don't typically make an acid iodide. Now, the most common one to make, and you guys are actually going to make it next week in the off lab, is the acid chloride. This is the most common one. It is the most reactive one. You're making these typically because you want to use them to do something else. It's very, very rare to make an acid halide, put a cap on it, and keep it around for a while. Usually you make it, and then you add something to it right away. So, if you're going to go through the trouble of making one because you want to add something to it right away, you're not going to make one that's less reactive, right? That's kind of defeating the purpose. So since this one is the most reactive, the next step is probably going to work better. So acid bromides will work, they're just not as good. Acid iodides, they aren't that reactive, so they're not that great. So no one makes them. In terms of the reactivity of either one of them, there's your halogen right there. The halogen is electronegative. So we have an electronegative atom right here. And so it is pulling electron density towards itself. What that's doing is that is creating on the carbon that the nucleophiles are going to attack, it's creating a really large delta plus. And what this means is that good nucleophiles can definitely attack. Like if you put a Grignard in there, it's definitely going to attack. Grignards attack anything, right? So it doesn't matter. But poor nucleophiles will also attack. So basically, anything attacks. Because of that, these things are pretty unstable. When you guys make it, we're going to put a drying tube on there. We're going to be pretty careful. We're not going to be as careful as we were with a Grignard. But still, you're not going to want your glassware wet because water, which is a nucleophile, would be in there. We're going to take some precautions to make sure that no stray nucleophiles get in there, other than what we want. Okay? Since any kind of nucleophile will attack it, we're going to see no catalyst needed. We are just going to toss nucleophiles into this reaction and get products out of it, okay, without a catalyst. So let's go ahead and make an amide. This is the one I told you last unit. Just memorize this reaction. We'll learn the mechanism later. Oh, time has come. So, reactions. Number one, conversion to amides. Okay, let's just go ahead and put up a reaction, and then we'll just do the mechanism on this one. So I make that acid chloride. And let's make a secondary amide. So we will add to it a nitrogen that has an R group on it. And let's put an ethyl on there. And I'm going to be lazy. And when I go through the mechanism, I'm just going to call that ET. It's easier to write. Okay. So here we go. This is really reactive, large delta plus right here. The nitrogen has lone pair electrons on it, and they are going to attack the acid chloride carbonyl. Electrons will go up onto the oxygen, and we get a tetrahedral intermediate with a CO minus. And the nitrogen is now on there. The nitrogen now has a plus charge. So what has to happen at some point in the mechanism is I have to get rid of the plus charge. So I need something that can function as a base. And I could have this come down, kick out a CO minus. CO minus is not that effective of a base. And so what people often do, and this is what we're going to do next week in the reaction, is you add some purity. You guys will actually be adding a drop or two of purity into your reaction that provides us a base. That you come take that H plus. So, let's have purity come do that. Generally, in these reactions, you will see some kind of base added to help out with this. Okay, we're almost there. We're going to reform the carbonyl. Electrons come down, chlorine gets kicked out. It's a good leading group, so there's no problem doing this at all. This reaction occurs really easily. So these acid halides have a couple things going for them. A pretty reactive carbonyl and then a good leading group. So everything's set up for reactions to go really easily. Okay, let's look at another one. This one is also a fairly common reaction. This is hydrolysis. So this is reaction with water. So, let's just put up the reaction. We're going to get a carboxylic acid out in the urine. All right, so it's the exact same mechanism. My nucleophile is not that great, but I don't care. It's a nucleophile. It attacks. Electrons go up onto the oxygen. Minus Cl. And I have O. H2 plus.
More purity.
Yeah, if I wanted this to go really well, I could add some purity, right? Otherwise, I could just kind of wait around, see if the Cl gets kicked off and takes care of it. This happens even without purity, but it's just, if you want to facilitate it, put a good base in there.
Can water take the H off or not?
Water can take it off as well, yeah. And same thing over here. Amines are good bases, it can take it off too.
Yeah.
But typically they will add one, because otherwise you're using some of your reactant to
Yeah.
function as base. You don't want to do that. Okay? So, let's say we added purity, because we really want this to go really well. Purity takes it off. Minus Cl, OH. Electrons come down, kick out chlorine, and we have created a carboxylic acid. This works really, really well. It's also a reaction you would never do. Okay, this reaction, if it happens, it is, in general, a sad thing. It's not good. Why?
Because you created the whole point is to
How did
create
you
the,
get your acid chloride to begin with?
from a carboxylic
From
acid.
the carboxylic acid, you put thionyl chloride in, and then you treated it with water to get back what you started with, right? You would not do this, because you may as well do nothing at all and just go get some food or something, right? So this came from this. So this is a reaction that usually happens. It kills the acid chloride, and it's because you have used some wet glassware. This is where this reaction most commonly happens. As you wash something, you get it good and clean, it's wet, you put your acid in there, you make your acid chloride, and it instantaneously gets hydrolyzed. It's not what you want. So although it happens really well, synthetically it's not useful at all.
Turn me off on dryer glassware.
All right, here's one that is useful. reaction with alcohol. Alcoholysis. It sounds like something that would kill you. It's alcoholysis.
Same thing.
Reaction with ROH. And this is synthetically useful. If I take, let's just put up a very generic reaction. There's my acid chloride, and I'm going to treat it with an alcohol. I'll say it has an R prime group on it. I'm going to want to add some pyridine, help things out. Guess what the product is, based on the two things we've seen so far.
Both water.
It's an ester, good. And the byproduct is going to be, you'll be left behind with HCl, which is neutralized by the base. So if you want it all balanced, there it is. So this is actually a way of making esters. Let's go ahead. Want to do a mechanism real quick?
Yes, please.
I see half people, yes. Well, let's just do one super fast.
Yes, please.
We'll do a baby acid chloride, and we'll do a methanol. Okay, it's the exact same as the water. Oxygen attacks, electrons go up. We have O minus, Cl. And your alcohol now has plus charge. We would add base to get rid of the hydrogen. So pyridine grabs the base. And then electrons come down, kick out chlorine. And there's your ester. So you can see a trend. Already, we just looked at 3 of them, and you guys are able to predict what's going to happen. It's always the same mechanism. Okay, electrons. Something attacks, electrons go up, they come down, chlorine gets kicked off. It's just throwing different nucleophiles at it. Okay, let's do another one. And I'm going to see what you can do with it. There is a slight trick to this one. The mechanism itself is not a trick. I want you to see if you can figure out what the final product would be. So this would be 4. This is reaction with Grignards, RMGX, or alkyl lithiums, RLI. Remember, both of these are sources of what is effectively acting as an alkyl anion. Right, that's what they're sources of. Yes?
How did you get lithium on there? I don't know if you went over the reaction.
Oh, yeah, I think it's a 420 thing. What you do is you take an alkyl bromide and you react it with 2 equivalents of lithium metal, and you have RLI and LiBr. Typically, what you really do is you buy it in a bottle pre-made. But if you had to make it, that's how it's going to do it. Okay, so I want you guys, let's put up an acid chloride, and let's treat it with ethyl magnesium bromide in ether, and then we'll add H3O plus at the end, and we'll work up. And the key thing I'm going to add here is excess. Okay, there is more than one equivalent of Grignard. So quickly work through the mechanism, and when you figure it out, don't yell it. Okay, and see if you can figure out what the product is. got it? What's the functional group I'm left with at the end? An alcohol. It's actually an alcohol. Okay, let's figure out how that happened. If I'm using an excess, that's a hint. Whenever you see like the number two equivalents, 2 moles, excess, that is implying, when it's a reagent like this, that you are doing more than one reaction. Because there's no real need to add excess Grignard if it's only going to add once. So that's implying you're going to make something that is going to react again. So, with that in mind, we attack with the ethyl group. We end up with same mechanism as before, only the nucleophile is now an ethyl that's attached. I don't have to worry about pulling a hydrogen off of it because here is a, so it just attaches and I'm done. Electrons come down, kick out chlorine. And I have that, I have a ketone. Right? How many people got to that point? Okay, what do Grignards do with ketones? They react again, exactly. So this guy reacts with R minus again. Electrons push up. So now I have 2 atoms on there.
And they use the plus fix them.
And I cannot reform my C double bond O now because I would need a leaving group. So I'd have to kick out an ethyl group or the cyclohexyl group, and I'm not going to do that. So it just sits there, it stops. And you have your H3O plus step, and you end up making a tertiary alcohol. So when you treat acid chlorides with Grignards or alkylolithiums, you first get a ketone, which reacts further to give you a tertiary alcohol. Now, if you just want a ketone, the way I have this laid out, it is not going to work. I could try to do just one equivalent, try to limit it that way, but the problem I'm going to run into is that as the ketone builds up, it's going to start reacting with Grignard reagents, right? The Grignard reacts really well with ketones and acid chlorides. So if you try to control it by just doing one equivalent of Grignard, you get mixtures. I'll get some of this, which then when I hydrolyze it turns into the carboxylic acid. I'll get some of this, and I'll get some of this. It's not effective. But there is a way.
Could you,
Yeah?
could you use a lot of chloride?
I suppose you could. I suppose you could try excess chloride and see if you can't overwhelm it
Yeah.
that way, and then hydrolyze it. But then you still have to sort it out. Once you hydrolyze it, you'll have a lot of carboxylic acid you have to get rid of. Which you can, but it's not the best way. There's actually a reagent that will stop at the ketone, so it only adds 1. And that is, I'll just give it to you. It's a cuprate. Have we ever talked about cuprates before?
No.
Okay, now we time. They look like this, R2CuLi. The alkyl group is generally the same, it doesn't have to be though. Okay? And what these will do is they will deliver one alkyl group. They're less reactive than a Grignard. And they tend not to react with ketones and aldehydes. So, the way you make this, if I remember, is you take the alkyl lithium and you treat it with copper iodide, and you have 2 R2CuLi, and the 2 there, what is going to happen? Then I have lithium iodide, I think it's all balanced. I haven't balanced something in 15 years. See, R2, 2 Li's, a Cu, we're good, right?
Yes.
All right, okay. Oh, chemist of balance equations. There it is, that's how you make it. Okay, or you buy it, whichever. So, I am going to add to it ethyl, 2, CuLi in ether. And these guys do not add to ketones and aldehydes. So it goes there, I did that, and then it stops. no addition to ketones or aldehydes with cuprate. So it just stops it right there. Yes?
Could you potentially use this to make a tertiary alcohol with 2 different R groups on it? Like do that first and then do a Grignard second?
Yeah, you sure could. If you want to
Okay.
make tertiary alcohol with 2 different R groups, use a cuprate containing, say, an ethyl, then put an ethyl there. And then attack it with probyl Grignard. You
Mhm.
put probyl there. Okay, that'd be, certainly, yeah, that'd work. All right, so next time what's left to do is reduction. And then we'll continue, just write down our list.